Okay, so we're going to rebuild this with D flip-flops. We're going to start with the transition table, which is the same thing as the excitation table. So we're going to figure out what our D values are coming into the flip-flops. D1 is the same as Q1. And we're going to build it with a Karnaugh map that's just like we did with JKs. So this is going to be Q1, and this is going to be Q2, Q3. So when there are 0, the output's a 0. When there's 0, 0, 1, it's following X1. When it's 0, 1, 1, it's following X3. 0, 1, 1 is following X3. When it's 1, 0, 1, it's a 1. 1, 0, 1 is a 1. When it's 1, 0, 0, its output is a 0. So these are don't cares. So D1 is going to equal, well, let's make this a party right here. So that's going to be Q1 doesn't care. So it's going to be Q2 bar Q3 X1. Now we can make a party of these guys, or Q2 X3. And then finally, we've got one right here that's going to be Q2's changing its mind, Q3, so it's going to be Q1, Q3. Okay, D2. Q2 is 0. When there's 0, it's a 1 following this combo of X1 and X2. Okay, so it's a 1 when X1 bar X2. It's a 1 here, which is not X3. 1, 0, 1, it's a 0. And 1, 0, 0, it's still a 0. So these are the don't cares. Same don't cares as over here. So D2 is going to equal, well, we can make a party of these guys. Q1's not going to matter. Q3 is not going to matter. It's going to be Q2 X bar 3. All right, and then this guy looks like it's all by itself. So it's going to be Q1 bar Q2 bar Q3 X1 bar X2. Okay, so let's do Q3 plus D3. Okay, it's going to follow X1 in the 0, 0, 0 state. All right, in 0, 0, 1, Q3 is the opposite of X1. And then it's 1 here in 0, 1, 1. In 1, 0, 1, it's 0. And then in 1, 0, 0, it's 0. So D3, all right, let's do a big party here with this 1. So that's going to be, let's see, Q2, Q3 is changing its mind, Q2, and then we can have a party right here with X1. So that's going to be Q1 bar, and Q2 is changing its mind, so it's Q3 bar and X1. And then finally, we've got a implicant right here. So that's going to be Q1 bar, and X2 is changing its mind, X3 is a 1, Q3 is a 1, and then it's X1 bar. Looking at what the book did, this is the same. Here they managed to get rid of Q3. Here they substituted X2 for X1 bar. There's different ways to do these problems. We don't need to do the outputs again, these guys. So we're done. So here's what the book came up with. And you can see some of the differences right in here. These are the outputs. We did these when we did the JK flip-flops. And now what we could do is build this using a mux. If we're going to build it using the mux, we don't care about what these equations are. We really don't. None of these. So how are we going to build the mux? Well, it's pretty much the same way we built the Carnot maps. So we're going to have a mux for each one of these Carnot maps. So I'm going to start up here drawing them. So we're going to have 1, 2, 3, 4, 5, 6, 7, 8. So that's the 0, 1, 2, and this is the 7 line. And then we're going to have the 3 lines coming in. We're going to start off with the least significant over here, Q1, Q2, and Q3. So I'm just going to repeat that over and over and over again. Actually, these are wrong. I've got them backwards. But anyway, I'm going to draw them connecting these chips up. So we're going to imagine that this is Q1, this is Q2, and this is Q3. And they're sort of floating up underneath. So this blue line's underneath these chips. And these are the 3 present state Q lines. So this is Q1, this is Q2, and then this is Q3. I had them backwards. And the same thing's going to happen right here. And then it's really easy to hook up our muxes. 0, 1, 2, 3, 4, 5, 6, 7. So we just write these down. 0, x, 1, dash, x3, 0, 1, dash, dash. 0, x1 bar x2. So that's going to be an AND, or excuse me, an AND gate. And then dash, and then x3 bar. Then 0, 0, dash, dash. Then x1. Then x1 or x2, that's where this was different. And then dash, and then a 1. So we don't have to pay attention to this variable in a Carnot map and all that detail at the end of chapter 4. We don't have to turn this into an equation and straighten all that out. 0, 0, dash, dash. And then this one's going to be 1, 0, 1, 0, 0, dash, dash. And we're done. That's it for a mux. So now we just draw our 3 flip-flops. So we have our D input and our clock. And then we hook up our Q1 lines. I'm going to go all the way down to here. And then Q2, go to right there. And then Q3 is going to go to right here. And then this is Q1. So that's going to go down to right here. And then Q2 is going to go to the middle one. And then Q3 is going to go right here. And then we hook up our clock. All right, so all of this is correct. And what we can do is check our answers against the book. What you'll see here in the book is that they've added a 1, this enable line to each of these. Yeah, but that's incidental. So we're done. Now what we need to do is talk about the next steps after this. The biggest problem is async inputs. Here this is indicated by X with a star above it. We need to visualize the problems it causes. These blue boxes are hiding detail of an algorithmic state, and obviously X as an input is part of this state 1. But I wouldn't think of these as just an empty more box. Think of them as something going on in each of these states. And let's think of this input as a detector that's detecting a cruise missile flying by. And the goal of this system is to generate a defensive response. Now, on the input to our algorithmic state, we trigger on the rising edge. So this whole circuit right here only looks at its inputs for a brief instant. It opens its eyes just for a brief instant, looks at its inputs, and then starts responding. So it's blind most of the time. So if the cruise missile flies by just a little bit too early before this algorithmic state randomly opens its eyes, well, it's opening them on a clock pulse, but the cruise missile flying by is not timing itself with the clock of this synchronous circuit that's hanging around. So if the cruise missile flies by just before it opens its eyes, it's going to go right back right here. And even during the speed of light computation of the response of this algorithmic state machine, the cruise missile flies by. It's still going to go here because it's blind while it's processing all that data at the speed of light inside that algorithmic state. So it could go back to this state and never get to state 2, where you want it to be. There might be a output response that's generated right here that'll never get set. The good news is that there are logical ways to think about and solve these issues. What ultimately limits the speed of an algorithmic state machine is the speed of light. But before we talk about the speed of light, just the fact that one wire is longer than another wire causes a timing glitch. Those get exposed as you clock the machine faster and faster. The exercise of learning how to design an asynchronous state machine and then applying those design rules to a synchronous state machine enables that synchronous state machine to be clocked faster, to survive more of those glitches before it falls apart. So the next step is to study asynchronous machines and their design rules. The second point to make is that async does exist. If you think of a circuit in the middle, synchronous, it's dealing with the asynchronous world outside. It's dealing with input that's asynchronous, and it's dealing with output that has to be coordinated in an asynchronous world. So you're still going to have to deal with asynchronous out at the peripheries of your system. Your goal is to coordinate turning the motor on, looking at the encoder, stopping the motor at the right spot. The third point is that asynchronous machines are a little bit seductive. You're going to study how to design them, and you're going to go, wow, I could build a whole CPU out of this. It's sort of like a perpetual motion machine. Everybody knows that they can't exist, but still engineers go down to these deep, dark pits where they go, wow, nobody's really proven logically that they can't exist. And they keep trying to make perpetual motion machines and waste their lives. The same thing can happen if you start getting into asynchronous state machines. They appear to be possible, but nobody's going to pay you to do that. Your forefathers have gone down that deep, dark pit and gone insane many, many times. The fourth and final point is that you might hear the word async associated with studies of the human brain. The brain is indeed an async machine, but it's async in a totally different way. Every single design rule that we've had has been to avoid glitches. When you study asynchronous state machines, your goal is to avoid glitches. The brain actually lives on top of glitches. That's why there's something called brain waves. That's why if you study neuromorphic CPUs, they talk about spikes. They don't talk about ones and zeros. They talk about spikes circulating over in circles around in your brain. So it's the exact opposite of everything we've studied so far. Anyway, I hope I've encouraged you to take an asynchronous design class.